Hello and welcome to Tales from a Graybeard. I'm Dave, your Graybeard. Today I want to talk about microservices. I'm doing this because my friend George asked me to, and George is a great guy, and he introduced me to Valheim and Sons of the Forest and other great games, and he asked me, what are microservices? Because I was telling him that microservices aren't just small programs. And so I thought it was a little too much to just blast over Discord, so I told him that I would do a video and post it as part of my Tales from a Graybeard series. So this is my video on microservices. So what is a microservice? So yes, microservices are not just small services, but they are small services, just not just small services. They fill one specific need. This is really core to the difference between a microservice and a small monolith. A monolith serves the needs across a company. A microservice serves one particular need, which we call a domain, like a business domain. So that may be user management, customer management, order management, workflow, warehouse management, user interface. Any business can be broken down into these small chunks that can operate independently, and that's how we model microservices against the business need. They're horizontally scalable. That means that when you design microservices, you need to keep in mind that they're going to run in a cluster, and that you can add or remove parts of the cluster at any time. This leads to them being fault tolerant but high failure. And we'll go into the numbers for that, but basically it comes down to you have a lot of machines, they're going to die at a high rate, and so you're going to have a large number of failures, meaning that you have to be tolerant to those failures. And they're possibly asynchronous. I'll go into that more in later slides. So what is a monolith? As I said, it's a single computer application that performs the needs of a whole system. A system is typically a company, but it doesn't have to be, particularly if you're a larger company. They can rely on external services, external resources like databases, but think of it as one thing that does a lot. They're highly available. If it's a single computer application, you're going to want, if it goes down for any period of time, it's going to be terrible for the company. So you need to have highly available hardware. So in the old days, we used to have redundant power supplies, ECC memory chips, which are, they check the codes on it to make sure that the memory is correct. It has a parity bit. We would have sometimes redundant CPUs. We'd have RAID level drives, which is a system for doing redundant hard drives. So limited scalability, mostly vertical. If your business succeeded, you went out and bought a bigger computer. It was very hard to scale them, and the cost of buying bigger computers scaled faster than the performance. The cost of bigger hardware scales exponentially, but the performance scales linearly. Okay, so monoliths have some problems. So typically a monolith has a small number of servers as backup, usually just one backup, sometimes two, sometimes no backups at all. So what I used to do back in the monolith world is we would have one hot server, which was taking traffic, and we would keep one cold server there. So when the hot server went down, you would swap in the cold server by changing over DNS, and you'd be back up in the matter of a half hour if you were lucky. When a monolith crashes, just everything is fucked. Everything goes down, everything is just bad. Even with backup services, when you had the hot and the cold, when the hot went down, it still meant you were getting paged and were swapping in the cold normally manually. Bigger companies could swap in the cold automatically, but even then you would have downtime where the whole company was down for maybe minutes. But that cost additional money, and that was difficult to set up, and the things that did the swap over could crash themselves. You had developers working the same system. So there was one repository, this was back in the days of Subversion, and everybody's pushing to that same repository. And so it was very easy to have merge conflicts. And because it was all one big repository, you had very little separation between the code. So oftentimes you fix something here and it breaks something over here. They all push through the same Jenkins pipeline. So if you had 20 developers all working through the same system, you would often have Jenkins jobs piling up on top of each other. Everyone is in their same pager rotation because when the system goes down, it's the whole system. It's very hard to tell what part of the system went down. And so everybody had to know everything, and everybody was part of the same pager rotation. And nobody owns any problem because everybody owns every problem. In technical terms, these are the terms we use for this, had a poor separation of concerns and poor domain ownership. So separation of concerns was that problem when you break something here, you break something over here as well. Those concerns were not separated. And domain ownership means, very hard to have a team that just worked on user management and another team that just worked on owner management. Basically, everybody worked on everything. There's poor build pipeline management, Jenkins, everything goes through one build pipeline. That meant the more unit tests you have, the longer that pipeline got, the more difficult it was to get your code through. And so this is where I, as well as other people, had the no unit test philosophy. Or you run unit tests on your own machine. They don't run by CI/CD, which kind of destroy the whole purpose of unit tests. Poor release management, oh God. We used to have code freeze. Everyone would stop checking in while we built a new image to be released to the server. So you had your whole development team sitting on their hands for sometimes half a day every week waiting for the build to be built. And poor uptime, again, it relied one server with manual backups to it. And so you went down kind of frequently. Not every day, but once a month was pretty regular. And poor quality of life for the developers. You're getting paged, you're getting frustrated because you have to stop in the middle of your work to do a code freeze and a build. The release management, the build management, every time you try to change something, it required review from a million people because who knows what it would break. You didn't have proper unit tests to test all of it. It was pretty terrible. So microservices fix all that. You put the logic for one domain. Again, a domain is like user management, customer management. It's a business concern. You put all the logic for that domain and only that domain in a service. A service should just do that. And then you put a contract on top of that. You say, if you want to access this, this is how to do it. And typically that's an API. We'll get more into that later. It splits up the pipelines and the notification queues. So by pipelines, I mean build pipelines, and notification queues, I mean like pager queues. Pager notifications. So when you build, you're building just your thing. So you can make a Jenkins just for you. It doesn't matter. Your code is separate from everybody else's. Typically, you still have one centralized Jenkins, but now Jenkins can build, I think it's free version, can build 3 different pipelines at the same time. So it's triple as much code can get built as with a monolith. You can then pay for Jenkins and get as many as you have CPUs to support it. And again, you can have multiple Jenkins if you need even more power. But typically, you can also have a single Jenkins that drives multiple build machines, and so you can build it out to have hundreds of thousands of build queues all going at the same time. I don't know any company that does that, not even Google doesn't use Jenkins, but even they don't have hundreds of thousands going at the same time, but they'll have thousands going at the same time. It lets developers focus on their business domain and not worry about anyone else. Typically, you have a minimum of 5 servers, sometimes 5,000, but that doesn't mean it's 5 times the cost. You're doing virtual servers. When I was working for Verbo, our pricing service, after Chris fixed it up so that we could scale like this, it had about 125 or so in the dead of night, at our lowest time. And at our highest time of the day, at our highest time of the year, it went up to about 450 servers and would scale up and down like that totally smoothly. And because, at 450 servers, we'll go through the math in a bit, you're going to have downtime of one machine or another very frequently. So you go into it saying, this is going to die and we need to test it for reliability. And thus you have a much more reliable system. Okay, so I said we would go into the math for this. This is what I mean. Chaos engineering. So I think this comes from Netflix. The lore is that it comes from Netflix. I didn't actually find any proof of that. I went looking for it. I might have just missed it. But my understanding is it comes from Netflix. So think about it. If you have one machine, you might have 4 nines. Even at 5 nines, that means about 9 minutes, 8.7 something, I think, minutes per year of downtime. At 4 nines, which is much more realistic, at 5 nines, you need redundant everything. At 4 nines, it means redundant power supply, RAID disks, good quality RAM. And that gives you about 9 hours of downtime a year. You typically measure the cost of downtime in the millions per hour. So, depending on the size of the company, obviously. So 9 hours of downtime is big. When you have 100 machines, so think of this now in the microservice world where you don't have one machine, you have 100 machines. That means 900 hours of downtime per year. You can't run a company with 900 hours of downtime per year. That's ridiculous. So reliable hardware is no longer a strategy. You have to design for downtime. So chaos engineering, what it does is it is this philosophy that you have to design for downtime. And so you have to have systems that automatically are resilient and respond to downtime. Netflix made a product called Chaos Monkey, which will automatically introduce random problems in the system. Latency in the network, take servers offline, take whole clusters offline, and expect the business to continue. Now, Netflix is a big company. If you're on a smaller company doing microservices and a whole microservice goes down, you can't expect that business domain to continue. So if your order management goes down, you can't expect to be able to put in new orders or update old orders. But people should still be able to come see the website, should be able to search for product, should be able to talk to customer service. They should be able to update their own profiles. Most of the business outside of that particular domain should continue. Okay, so in the monolith world, this is what it looked like. You had the internet hitting a router, which hit your monolith. Really simple. Then we started to break up the monolith and started having these microservices, which really weren't microservices. They were small monoliths. And so the internet would hit a router, that would hit a gateway or aggregator. I used to use one called F1, which I'll be honest, I totally forget if that was the name of the company or the name of the product. But basically it was a router that could farm out requests to a different service underneath and could lock to the session so that you could design these microservices to be session aware and could maintain state, because that's how we did it in the monolith world. The problem then comes if one of these services go down, all of the sessions which are locked to that service lose their state, which typically means that they lost their order, they got logged out, and they're starting from the beginning, which at least the system is still running, they can go recreate their order, they can log in again, but it's still very jarring for the customer. So we went to a mesh network world. This is one where microservices know how to contact each other and know how to route requests as they come in. So the internet comes in, it hits a router, and that gets magically routed out to one of these machines in the microservice, and then the microservices themselves may be able to shuttle the load across different microservices. This is done through mesh networking. The product that I'm most familiar with is Linkerd. There are other products. I understand HA Proxy can do this. There's another one called Envoy. I've heard of a few others whose names escape me, but basically, they're a piece of software that runs on the local machine that has the microservice. The large gray box is the virtual server, virtual hardware. When the microservice needs to make a DNS request, it requests against the local host hitting Linkerd. Then Linkerd can do any sort of thing to go out and figure out what to respond. It's not your standard DNS. It can look it up in a shared database, typically etcd or consold. It can figure it out via round robin or whatever, however you want to set it up. It can figure out which of the many microservices to contact. But even more importantly is it's able to check a central registry to say which ones are down. So if it gets one and it says, oh, I contacted this one, it failed, it contacts the central registry and says, take that one out of your queue. And then the next time it goes and looks up for that service, that broken one won't be in the queue, it'll get a different one. And in this way, you're able to route around broken microservices. So when one goes down, it gets isolated, and then that gets notified to whatever your cluster management software is. And that cluster management software can drop it out, bring up a new instance, and bring it back into the service. So this is where we get fault tolerance from. All right, so let's talk about domain separation. So in this model, we're sort of still treating this microservice as a monolith. It's one microservice that handles the whole business. But this is not really how it's done. By the time you have this mesh networking, you have domain separation. So again, domains are business areas, subject specific, user management, order management, warehouse management, workflow, user interface, any of these chunks of the business. And every business is modeled differently. Every business has their own domains, but some domains are very common across businesses. User, customer management. Every e-commerce site has some form of user customer management. They all have some form of order management. Usually there's some sort of payment system. And these are all separate domains. Now, if you have one cluster per domain, you begin to look more like this. So the router comes in and naturally hits the UI, or the internet hits the router, and naturally it hits the UI, which is going to be stuff like the home page or the ordering page or the search page. And with larger companies, you don't have one UI business domain, you have a search UI business domain and a homepage UI business domain. And you can end up with like hundreds of these business domain specific microservices. The larger you are, the more of these you need. But for a small company, and for the sake of it being intelligible on slides, let's just go with UI. Then UI needs to talk to customer management. Hey, what's this person's profile? Needs to talk to order management. What orders has this person had? Maybe they click order. Maybe they want to go to their checkout, see their cart. And so they communicate between each other. They communicate using strong contracts. What's a strong contract? A contract is an API definition. It doesn't have to be APIs. We use the term contract to mean a lot of things, but in today's world, it means APIs. Actually, not necessarily. I'll get into a place where it doesn't mean APIs in a bit. But for this case, typically REST, GraphQL, gRPC, SOAP if you're a glutton for punishment, any sort of API where you can talk between machines. And again, they're using Linkerd. So when UI talks to order management, it's not talking to a centralized router. It's using Linkerd to figure out, hey, give me any one of these machines in this cluster. I don't care which one. Use whatever way you need to figure out which one to use. And it will then choose one of these, and it will enter the cluster. And it doesn't care. It just sees it all as one big virtual machine. And they can all talk among each other among these strong contracts. These strong contracts give you a really good aspect to it, which we'll talk later, but basically it gives you what's called loose coupling, which means that they're coupled together, they talk to each other, but they're coupled loosely so that they can operate independently. As long as no one is changing that contract, the people in order management, the developers working on order management, can do anything they want, as long as their contract stays the same. Same with UI, customer management. Any business domain has the right to operate entirely independently from the others until they need to change their contract, and it's only when they're changing their contract that they need to have these reviews and communications between teams. So I said there's one way that's not strictly an API, and that's asynchronous processing via message bus. So in here, UI talks to order management by making a REST call. Instead, what UI can do is say, okay, they click the purchase button. I'm going to post a purchase message onto a bus. And that purchase message will use the pub/sub model. It will publish a message onto the bus, and whoever is listening to it can subscribe to that. Pub is publish, sub is subscribe, can subscribe to that queue or channel, and will hear that message and will act on it. So the customer site may make a synchronous call to just check to make sure that this purchase is okay, there is inventory for it, there's nothing wrong with the account or whatever, and gets back a positive response, a really quick, like, yes, we have what we need there, and then we'll publish the actual order onto the queue. Then the order management side will pick it up and will do whatever it needs. It will decrement the inventory, it will increment that person's order, it'll start the payment system to recognize that there's a payment coming in. It will do whatever steps are necessary to fulfill that order. Now, that message is not strictly an API call, it's a message bus. So the contract there is the format of the message on the message bus. These message buses don't enforce a contract. You normally lay a layer on top of it. The current hotness in message buses is Kafka. That's a picture of Franz Kafka, for whom it is named after, down below there. I always enjoy that because he was one of my favorite authors in high school, and I still like his work quite a bit. Very few people actually know that's where it comes from. But there's others, RabbitMQ, ActiveMQ, a whole bunch of others. But Kafka is hot because it has some nice features. It's disk-backed, which means that you can roll back the queue and you can say replay from the beginning or replay from this point in time, which makes recovery a lot easier. And it has consumer groups. If we look here, you see each one of these has a lot of services in it. So if each of these is listening to a queue, it's very possible that two will pick up the same message and you'll get the order posted twice. If you use consumer groups, each of these microservices is a consumer and each of these clusters is a consumer group. It says, okay, we're only going to allow it to be read once per consumer group, but that allows you to have multiple subscribing groups to it. So you can have a group for data analytics that will keep track of how many orders are made and who makes them and what amount, and provide these analytics back to the business so they can run the reports. You can have one for logging and one for quality control, and you can have as many consumer groups as you want, but each group is guaranteed to read one and only one message at a time. And this is where Kafka really excels above Rabbit and Active. I bet that this feature is in some of those, but Kafka does it really, really well. Sometime in the future, maybe by the time I publish this message, there'll be a new hotness coming along, but it's going to have those basic features. Okay, so now it looks like this. The truth is there are still asynchronous calls between these systems, but as many calls as you can do within Kafka, that means that you are not waiting for the other system. So now if in this fake diagram where it's all through Kafka, if order management and customer management are just down 100%, UI continues to run. It's not depending on them at all. The truth is there will be some dependencies and you need to put in retries and asynchronous REST calls and whatever. There's ways of reducing the effect of synchronous calls between microservice clusters, but the more you can have Kafka, the better, the more loosely coupled these will be. Okay, so let's talk about some of these advantages. But just to quickly review, microservices are smaller pieces of code that are domain specific. They use mesh networking to represent a cluster as a single machine and to not make the services have to worry about how to connect to those machines. They use asynchronous processing wherever possible. And they use strong contracts. Oh, I forgot to mention, the strong contract system for Kafka is called Avro. It layers structured data on top, so you can publish Avro schemas, and that is your contract. But it uses strong contracts, that is API schemas, to communicate between them so that they can operate independently. I have it there. So it's one of the advantages is easier development. It's much easier to modify smaller applications. The smaller the application, the easier it is to fit in your head. The easier it is to develop, the easier it is to release and to build. Also, domain separation means it's harder to break other parts. You don't have that problem where you change something here and you break something here. More team autonomy. So teams still have to agree on contracts. But you can come up with a contract, you can come up with a schema, and then the team that's publishing the contract can come up with a sample, like example request and response, and then hand that off to the other teams, and they can use that to mock out their service. Now, UI is able to mock out order management, and so UI can continue developing without having to wait on order management any longer. Order management can take its time to implement that stuff because UI is off developing, they're running, they don't need anything from order management unless a question comes up. Oh, I have this use case, it's not in the contract. You go back, you revisit the contract. But the number of points of communication between those teams drops dramatically. Okay. And that also means that anything within the teams, as I was talking about, order management has total control over their own domains. So they don't need to have sign-offs from some big architect that knows the whole system. Order management can do order management as long as they don't affect the contract between the services. Okay, let's stop and take a break and talk about return to office. I see a lot of people in Reddit, on Twitter, whatever, saying that return to office is driven by people who have bought a lot of real estate and don't want to admit their mistakes. And there's probably some of that. It comes from managers who who can't manage their team unless they don't see them, or unless they do see them. Sure, there's probably some of that as well. But that's not the primary driver. The primary driver comes from when teams have to communicate among themselves. In this situation, if you don't have strong contracts, or even worse, in this situation where everybody's in the same application, your teams need to communicate a lot. And that sort of communication, it's hard to communicate well among a broad group of people when your communication mechanism is best for point to point. We've all been on big Zoom meetings, and trying to get everybody involved in the same big Zoom meeting is really, really tough. It's just better one-on-one. If you want to communicate well between teams, or just between individuals that you don't know well, being face-to-face is the best way to do that. You go out to lunch together, you play ping pong together, you have coffee together, you go to the bathroom and you come out and you're washing your hands at the sink together. You know, that you interact when you're in the office together. The key to not needing that is to put in these strong contracts so the only people you need to have that high level of communication with are people within your business domain. Now you're communicating with 3 to 5 people instead of communicating with 300 to 500 people. And that means that you can operate much more efficiently at home. If you don't have these strong contracts, if your application's not split up like this, eventually your managers are going to tell you that you need to be back in the office, because getting everybody on the same page and making sure that your software actually works at the end of the day becomes increasingly difficult as you have more and more people that have never talked to each other. I mean, in person. That have never eaten lunch, that have never hung out as a group. So, one advantage of doing proper microservices with strong contracts and loose coupling and domain separation is that you don't have to come back into the office, that you can work properly from home. This isn't the office, in case it's not obvious. And this is why this is able to work. Oh, that was the slide. Okay. So fewer and easier pages, meaning PagerDuty, not like pages in a book. So it's easier when the order management application goes down. Now you've got 3 to 5 people to figure out who is, and it's whoever's on PagerDuty. You know, everybody in order management knows how order management works. So it's much easier to figure out what team owns the problem, because it's whatever service went down. It means you generally only get paged for your team. Now, when I was working for Verbo, we had very good domain separation, and we would still get paged for a lot of stuff because I was on the pricing team. When we generated a price, if it didn't show up right on the web page, they paged the pricing team. Okay, sometimes there was a problem in the web page that just wasn't like retrieving the price right or whatever. It's not a silver bullet, but it's much better. And so it also leads to a lot less of, let's just get everyone on the page. Let's just page everyone, get us all on a call, and figure this all out. I think in my time at Verbo, we probably had 4 or 5 times where we needed to have one of those massive everybody on the page. And that included 2 separate times where we had some big public event and the systems just crumbled under the weight. And everybody was down. It wasn't a matter of not being able to figure it out. Like, everything was broken. So they're also more failure resistant. I forgot to talk about red-green deploys, and that's a picture of red-green from the red-green show. Red-green deploys mean that you can have a green cluster that is up and running. You can bring up a red cluster that's not, run tests against it, shadow traffic to it, test it however you want, and even bleed traffic over to it slowly, all in an automated fashion. So when you do a deploy, instead of having to take the green one down, be down for 30 seconds, and then bring the red one up, what you can do is have a slow, smooth move over from green to red after you know the red cluster is all good. Then once the red cluster is fully green, you ditch the green cluster and you move on. Scaling, this one's really famous. Microservices scale really easily. As I was talking about in Verbo, we could scale from 125-ish up to 500 in the blink of an eye. All automated. We didn't touch it. Now there was a problem here. We scaled according to CPU utilization because we were a CPU intensive application. That meant if we released something that was inefficient and added to our CPU, we wouldn't notice it. It would just scale up. And the only way we would notice it is if the report manager, me, would go and look at our Amazon costs, and which we had a nice dashboard for, and would see that we spiked the previous day. And then I'd have to go and explain what happened to my boss, who would explain it to the finance team. It was a big mess. But honestly, I'd much rather have to explain to Peter why we didn't meet our numbers again, rather than having the whole thing to go down. Oh, and that is my last slide. I need to start putting an end slide in these. Thank you very much for listening. This has been another Tales from a Graybeard. I really appreciate everybody joining me for this. If you have any questions, any comments, stories about when microservices worked or didn't work for you, please put them into the YouTube comments. I'm very interested in that sort of back and forth. So thank you very much, and I hope to see you again.